video.
Let's start, everybody. Hello, everyone, and welcome to this week's colloquium. Pay attention. So we are pleased to have Dr. Sushant Dutta. He's an IDIA postdoctoral fellow at UCT. And he's going to talk about the spectral age estimates of remnant radio galaxies in XMM-LSS field. Thank you, Sushant, for accepting our invitation. And the floor is yours.
Good morning, everyone. So today I'll be talking about spectral age estimates of remnant radio galaxies. So first I'll talk about what are radio galaxies, a brief introduction about radio galaxies. Then I'll talk about what are remnant radio galaxies. Then I'll come to how do we do the spectral age analysis of these objects. So a brief intro about radio galaxies. So basically radio galaxies are a subclass of active galaxies. So active galaxies means AGNs. So a radio galaxy has a typical morphology where it consists of a core, which is active galactic nuclei at the center, and it has a highly collimated jets and a radio lobe, which is nothing but a cocoon of plasma. And then at the edge of this plasma, which we call radio lobe, we have hotspots. So this is a typical morphology of a radio galaxy, and this phase of a radio galaxy is known as active phase. So this active phase, like it goes from 10⁷ to 10⁸ years, like tens of or 200 million years. But what happens once this active galactic nuclei or the AGN switches off? So that means when the activity ceases, then then you won't be able to observe the core. There won't be any jets, and there won't be any hotspots. Only radio lobes will be seen at this stage, and this stage is known as the remnant phase of the radio galaxy evolution. So in this stage, so a remnant radio galaxy morphologically it will look like something like this. Only radio lobes will be seen. So the background is an optical image taken from Subaru I-band image, and so you can see only relic radio lobes, and at the center there is a potential optical host. So in this remnant phase, the radio spectrum shows a strong spectral curvature, like this. So I'll talk more about this spectral curvature. How does it look, and how it affects the different phases of remnant radio galaxy evolution. But first of all, let's talk about how do radio galaxies evolve. So radio galaxies basically evolve as we human do. So at the time of the birth of a radio galaxy, it's a very small. It has a compact size, and it slowly evolves over the time, and its radio luminosity also increases with as the source evolves. So it increases in size as well as in luminosity. So this phase is known as the young phase of the radio galaxy evolution, and then it reaches to a certain evolutionary phase when it exceeds a particular size or a particular size. So this is around like 4 to 40 kiloparsec. When it reaches this critical limit, and basically this critical limit is not a sharp limit, it varies from source to source. So when it reaches this limit, then we call it as an evolved phase. It starts in the like evolved phase of radio galaxy evolution. Then it evolves more, then it enters into the fully evolved FR1 or FR2 radio galaxies, and then it starts to lose its radio power, or that means it loses its radiation via synchrotron or inverse Compton scattering. And then it enters in the remnant phase at the last, and this remnant phase is the last stage of a radio galaxy evolution. So this is how a radio galaxy evolves in its life cycle. And this is a widely accepted theory of how radio galaxies evolve. So in a nutshell, radio galaxies, when they are in a young phase, they go in a adult phase after like they evolve in size and they evolve in luminosity. They enter in the adult phase, and then from adult phase they enter into the remnant phase. And in some cases, the due to some Wallin phenomena, the remnant phase can again go into an active phase. So it will enter from remnant phase to a restarted phase, where you will see again a core, highly collimated jets and hotspots, and you will also see the remnant lobes at the outer parts of the young radio galaxies. So I won't talk about this restarted phase, but I will be focusing on the remnant radio galaxies and how do we characterize them, how do we identify them. So the main question here is, why do we care about these remnant radio galaxies? So we have some unanswered questions which we need to address. So first one is, we actually don't know in active radio galaxies how do the jets evolve, or how long this activity goes on. We don't know the how do in the cessation period, how do the remnant lobes evolve, because there is no fuel left in the remnant lobes, only the electrons, or the what do you call that, the plasma, which is remnant. Or so how does it evolve, how does it grow as the source evolves? We also don't know how often this switch on and switch off thing goes on, because we don't know the AGN duty cycle. We want to know the AGN duty cycle of these objects. Also, the main and important question is, we want to know about the intrinsic jet power and intrinsic jet power of a radio galaxy, and how does it affects the surrounding and ambient environment. Basically, the feedback process of a radio galaxy. We want to know this mechanism with the time in the cosmic evolution, and with the jet power, with the luminosity. And we want to know this large scale environment with in a clustered medium and a non-clustered medium both. So to address these questions, we need statistics of remnant radio galaxies, because see, the last phase of like we in human life cycle, we do well, like if you want to know that how life evolves, so you can't ask to a kid, you have to ask some elderly people, right? So they can tell you that, okay, life starts from there, and then it enters in the adult phase, and then it goes to this phase, and life ends like this. So likewise, here we want to study remnant radio galaxies, and they can tell you, and we can trace back to the very initial phase of radio galaxies, and then we can get the entire evolutionary structure of how radio galaxies evolve, and what are the possible mechanisms going on inside the radio jets and radio lobes. Okay, so the main part is that we want to get statistics of remnant radio galaxies to get a statistical trend of how these objects evolve. But the only problem is that they are rare, and they are thought to be rare initially, but now we know that, okay, this is a sensitivity limited thing. So we don't have much sensitivity, because as I showed you initially, that the luminosity drops here. So they are faint, and they have very diffused structure. So you must have a very sensitive, a very with a high precision, high angular resolution telescope to observe these structures. So so they were thought to be rare, but now we know that they are actually not rare, just because we don't have enough sensitivity in our radio telescopes. So we don't have enough population of these objects. But now the question comes, how do we identify them? So we have some basic selection criteria. So first one, obviously on the basis of radiomorphology, as I said, that we don't see a core, we don't see hotspot, we don't see the jets. So if you see such structures, then we call them remnant radio galaxies. So as I said, that AGN, and also the AGN emits in all the frequencies. So the AGN should be absent in all frequencies, basically. So not only in radio, like starting from X-ray to radio. So it should be absent in all frequencies. And if to confirm, we want to confirm the presence or absence of radio core. So for that, we need high resolution radio observations as well as the sensitive observations. So high angular resolution means we can go till like 3 gigahertz or 1.4 gigahertz radio observations. For sensitivity, we have to go like down to like sub-microjansky level. So where we can like confirm, we can confirm ourselves that okay, there is no radio core. But see, it is, as I said, it is sensitivity limited or flux limited observations always. So we cannot rule out the possibility that there could be a very faint radio core at the center of the radio galaxy. So like here you can see that there, so these green radio lobes are overlaid on top of a optical image. So this optical image is taken from a VLT, and the center is the potential host galaxy. And yeah, another thing that these radio lobes are often accompanied by or associated with a diffuse low surface brightness objects. Like these objects are basically radio lobes. So these would be in remnant phase, these would be amorphous, low surface brightness, and diffuse emissions. So this is how you morphologically you can characterize them. But this could be like sometimes evasive. If you see some core here, or if you see some bridging emission here, so it can be like evasive somehow, that okay, morphologically we can't say that for sure that it is indeed a remnant radio galaxy or not. So for that we have a conclusive selection criteria, which is based on spectral curvature. So as I said, that in remnant phase radio galaxies show a strong curvature in their radio SEDs. So what are radio SED? It is a plot between flux density and frequency. So in the cessation phase, or in the remnant phase, we know that there won't be any AGN, so there won't be jets. So that means the fresh particle injection to the radio lobes won't be there. So then there will be a spectral break in the radio SED, and this spectral break will shift towards the lower frequency as the source ages, right? And so as the source evolves, this curvature will be so at the higher frequency side, you won't observe any like any component, like no compact object. You won't see any compact object, like no core, no hotspots, no jets, nothing. And eventually the radio lobes will also disappear after a certain duration, but that duration is actually very short. We found that it is actually very short duration. So between that time scale, you have to observe that object, and you have to study on them, you have to characterize them. So this short duration is around 10 to 100 million years at most. But nowadays we know that because so in our study we found that this time scale is even shorter, even like 1 to like 20 or 30 million years, even very shorter, right? So, and yeah, of course, because there are radiative losses in the cessation phase. So radiative losses means it will depend on the magnetic field as well as it will depend on the energy. So high energy photons will lose their energy faster, as we know that. So, and on top of that, it will lose its energy via radiation, like synchrotron and inverse Compton scattering of CMB photons. Okay, so both of them will create this spectral break, and this spectral break will go down and down, like down to low frequencies. So that's where we can see that the importance of low frequency radio observations are needed to search and identify remnant radio galaxies. Okay, so now talking about spectral aging analysis of remnant radio galaxies. I will talk about multi-frequency radio observation in the later part. How do we actually search and characterize these remnant radio galaxies? But before that, because I'll be talking about spectral aging analysis, like my focus will be on spectral aging analysis of remnant. So just to give you a brief idea, how do we do this kind of study? So basically, we know that the radio source show spectral break in their evolved phases. So this spectral break can be related to the age of a radio source with this formula, where equipartition magnetic field plays a main role. So this equipartition magnetic field, and in combination with CMB magnetic field, we can estimate, and obviously we have to know the redshift of the source using optical photometry or spectroscopy. So we prefer spectroscopic redshifts for that. So everything you can know, equipartition magnetic field, CMB magnetic field, and redshift by observations, but you can't get this value which we called bit frequency using observations. So to get this value, we need modeling. So we have some spectral aging models or spectral fitting models which can give you this value, and then we can estimate the age of a radio source. And once we get this total age of a source, we can estimate the off period. Off period means the remnant duration and the active duration. So the equipartition magnetic field is estimated by this formula, where this minimum energy condition is given by this horrendous looking formula. So we need some model. Now this model, what we use, is a continuous injection off model, which takes care of the remnant duration, the active duration, the magnetic fields, and the equipartition, as well as the minimum energy magnetic fields, and the break frequency. It gives you the break frequency as well. So there are certain models, spectral aging models, which are pretty standard, and we have initially in initial days, like in 90s till 90s, we had these models, JP, KP, and treble models. So basically, KP is from, like, they were astronomers, Kardashev and Pashologists. So they proposed a model, a spectral aging model, which they assumed that the synchrotron spectrum is arising because of a bunch of electrons are going at a time from core to the lobe. So like they assumed that all the electron population from the core are going to the lobe at a time, not continuously. So that was the first flaw. Or later on, people identified this flaw because this seems very unrealistic, that all the electron population is going at a time. So it should be continuous thing. So then people observed this flaw, and then they came up with a new model, which is called continuous injection model, where the electron population is going from core to the lobe continuously. And so there are two models, which is first one is CI-ON, which is for active sources, and CI-OFF, which is for active as well as the remnant sources. So we get this off period, we get the total time, total duration of the radio galaxy, and we also get the break frequency from these models. Okay, so how does the radioacity looks like in the remnant phase? This looks like this, where we get the a curvature here in the radioacity, and this curvature is because there is no replenishment of fresh particles in the lobe. So we use to get this kind of radioacity, we use broadband radio astronomy tools or BRATS, and we use, as I said, we use CIOFF model. So what we have to give from our side, so input parameters are injection index. So injection index means initially what was the slope of the radioacity. And by meaning of slope, I mean that what was the synchrotron radiation loss at in the active phase, or in the active period. So basically, synchrotron itself loses some energy in the active phase itself, right? So it will have some slope and in the initial phase, and when it enters in the remnant phase, it will give you another slope which will be steeper than the initial one. So we take the difference between this alpha 2 and alpha 1. Alpha 2 is the later the slope of in the remnant phase, and the alpha 1 is the initial injection index, or basically the slope at like in the active phase. So we have to estimate, we have to input injection index, as well as we have to give the magnetic field estimate. So this magnetic field is only the equipartition magnetic field. And so it yields spectral age, so to total spectral age of the source. It yields active phase as well as the remnant duration. It also gives you the reduced chi-square value. So yeah, this is how spectral aging analysis is done in case of remnant radio galaxies. So now let's talk about the multi-frequency radio observation needed to search and identify remnant radio galaxies. So we actually use the low frequency observations, radio observations, because as I said that the spectral break is will move towards the lower frequencies as the source evolves. So we have to get all the low frequency radio observations starting from very low, like 150 megahertz to like 1.4 gigahertz, and higher frequencies to confirm the absence or presence of the radio core. So we will use LOFAR, uGMRT, MeerKAT, and JVLA, what we have. So here you can see that we not only need multi-frequency radio data, but we also need sensitive data. So here you can see the sensitivity of what we use here is of sub-microjansky, like it is reaching around 2 or 3 or 4 microjansky. So this is the level of sensitivity we need to identify those faint radio emissions. So why we need multi-frequency radio observations? Because we want to populate this radio SED with as many points as possible, so that we can constrain the spectral age like robustly. Okay, so just to give you a brief idea of what MeerKAT is doing and what are the character, like what is MeerKAT. Just to give you, we have 64 antennas, and it is located at the northern Cape of South Africa, and each dish has a diameter of 13.5 meter, and we usually use central core. So central core has 48 dishes. And because why do we need central core? Because we want to estimate the large scale structures. So the central core will give you the extended structures. Okay, and we will, so we have UHF band, L band, S band. So in deep fields, there are no such surveys in UHF band. but we have a L-band survey in deep fields, what we call MIGHTY. So talking just a brief intro about MIGHTY. What is MIGHTY? MIGHTY stands for MeerKAT International Gigahertz Tiered Extragalactic Exploration. So MIGHTY has been observed in 4 deep fields: the Cosmos, XMM-LSS, ECDFS, and LSS1. So I'll be focusing on the XMM-LSS field only, and it reaches up to like 1 microjansky, or I would say some microjansky resolution at 6 arcsecond. And so, what are the main scientific goals for this survey? So it is basically used for to know the evolution of AGN and star forming activity, and to know the evolution of neutral hydrogen and the properties of cosmic magnetic fields. So these are just the pointings of different fields. So these yellow pointings are MeerKAT. So I'll be focusing on these pointings. On top of that, so MeerKAT is at higher frequency, that is L-band of 1.4 to 1.28 gigahertz. But to complement that, we also have super MIGHTY data, which is taken from uGMRT. So this complementary radio data is taken at band 3 uGMRT and band 4, which is at lower frequency. So we have the complete coverage from low frequencies to high frequencies. So in this survey from uGMRT, we have a survey from at band 3 and band 4 both. So these are the footprints of Cosmos as well as XMM-LSS. So these the black one is band 4, and band 3 has been shown with green. And yeah, you can see that in XMM-LSS field, we have at minus 0.4 robustness, we have reached minimum noise or minimum RMS of 4 or 5 microjansky, which is quite like good for to estimate the sensitivity, to at least reach the sensitivity level of MIGHTY as well. So which can give us a clear indication of whether we can detect a diffuse radio emission or not. And yeah, so what we used all these starting all these radio observation, multi-frequency radio observation, and yeah, these are the footprints of all the radio observations we used, and these crosses are basically the overlapped sources of remnant. So here we have identified only 14 remnant sources. So these are not confirmed radio source remnant radio sources, but these are candidates. So so basically we want to confirm whether these remnant candidates are indeed in remnant phase or not. So for that, we need to have a radio SED, which will give you a strong curvature and which will show diffuse low surface brightness without core morphology, right? Okay. So our remnant sample is something like that, and you can see that our sources particularly lie at the high redshifts. So you can see that our redshifts can go up to 2.8 and or so on. So these mostly reside at higher redshifts, and since they are at high redshifts, so you know that at high redshift the CMB photon density is higher. So that means the IC-CMB or inverse content scattering by the CMB photons are higher at the higher redshifts. So that means they will lose their energy faster. So that's why the remnant duration is very short. Okay, so how did we came up with the sample? So we already had identified these samples, these sources in our 2 papers, and we gleaned this new sample from these 2 papers, and basically these 2 papers suggest all the like all the remnant candidates available in XMM-LSS field, and we want to now confirm with multi-frequency data whether they are genuine remnants or not. And we then convert all the images from these multi-frequencies with a circular beam of 11 arcsecond, and we smoothed our data, we regrid our data, and then we estimated the flux densities at different frequencies. And then we came up with this SED. So we used BRATS again to model our radio SED. Now, earlier we had only 4 data points, as you remember, if you remember with the, yeah, that we had only 4 data points, the LOFAR one, the GMRT one, then we had uGMRT one at 400 megahertz, and then we had JVLA. Now we have 6 data points. So starting from LOFAR to 1.5 gigahertz JVLA. So now we can constrain our spectral age much better, much like robustly compared to the previous papers. And so as I said, that we have to just input injection index and magnetic field, and we will get all these things. So now you can see that we have morphology as well, but morphology can give you a wrong interpretation that, okay, this looks like an active source, because it doesn't show you a clear double lobe structure, right? So that's how this spectral curvature criteria give you a conclusive evidence that it is indeed remnant radio galaxies. So another case is that here you can see a clear radio core at L band, mighty L band, but the spectral curvatures suggest you that no, it is indeed a genuine remnant, not a active. But we have already compared, we have also compared our sources, our sample sources with the remnant sources reported in literature. So here you can see that all these sources in literature have higher spectral age, but our sources are mostly residing in the lower spectral age part. So this regime, we are basically probing the very faint regime, and where they are residing at very high redshift, and they are, as I said, that the inverse Compton scattering will be more at the higher redshift because of higher density of CMB photons. So they will have a shorter remnant duration, right? Okay. Now we also estimated spectral ages using spectral age maps. Again, we did all these analysis using BRATS. So it gives you pixel by pixel spectral age estimates, because it calculates like the flux density at each pixel, and then it gives you the entire spatially resolved spectral age maps. And these spectral age maps will give you a slight idea about how does it evolve. Like here you can see that it is a small angular scale remnant, where you won't be able to see that, okay, whether it is actually a remnant or not, because it looks like just a blob, right? Just a blob of plasma. So you won't tell like that it is indeed a genuine remnant or not. So, but here in the spectral age map, you can see that there is a gradient of spectral age. So like this one is like a relatively newer regime, and this one is pretty old. So basically it tells you that the gradient of spectral age suggests that this portion of this radio galaxy or remnant is towards, it's away from you. It's basically receding, and this one is towards us, right? And again, this one also suggests you that this part is going to coming towards us, and this one is going away from us, right? And the spectral ages, you can see that they are very low, like minimum spectral age is around 2.21 and maximum is 5.81. So that means within 5 or 6 million years, these objects vanishes, right? So that's the main point, that they are rare because they are of very short duration. That's the the new finding we got in our papers. So to summarize my talk, remnants are rare and it depends on the sensitivity of the radio surveys. And we included sensitive and high resolution radio data, multi-frequency radio data using SuperMIT and MIT, which helps us to constrain spectral age estimates robustly. And we use CIOFF models to generate radio SED. And this study acts as a test bed for upcoming SKA and its pathfinder. So basically, SKA will have more coverage, more like depth. Its depth will be unprecedented. Its sensitivity will be like what we need to identify and search remnant radio galaxies. So that's all from my side.
Thank you so much.
Thank you.
Great talk.
Yeah.
Interesting work. Any questions?
Yeah.
So is it worth comparing? Do you see anything sort of in other wavelengths such as X-ray maybe? Of these things, I know the radio galaxies, like the diffuse stuff.
Yeah.
Is very radio specific, right?
So basically, as I said, that the radio core will be absent at all the frequencies. So remnant radio galaxies won't be observed in any wavelengths. So in X-ray, basically you see only the AGN part, right? Not the so yeah, if they are active, then you can observe the core, the jets in X-ray somewhat. But in remnant phase, only the radio lobes will be seen, right? So you can't observe them in other wavelengths. So that's why we are using multi-frequency radio observation only. And optical obviously is used to identify the potential host. Yeah.
Okay, I see that. Let's answer Abhishek's question.
Okay.
Abhishek, you can just unmute and ask your question.
Thanks, Angus. Thanks, Susan, for the nice talk. So you said there is this fading timescale of these remnants, right? So what physical mechanism determine the fading timescale of RRGs? And then how sensitive are they to the local ICM or IGM conditions? Because these lobes would be traveling to the IGM and ICM, because I can see it is 1 megaparsec or so.
Yeah. So the feedback basically, or the large scale environment will affect the expansion of these lobes. So basically, if they are in clustered medium, then they will be trapped in the medium itself. So they won't. So you won't get the extended objects, like they won't grow to up to megaparsec scale. They will be trapped within, like say, kiloparsec scale. So basically, if large scale environment will be like dense enough, so then only spectral curvature will give you a conclusive evidence rather than the morphological criteria. So basically, your question is basically answered on the basis of the intrinsic jet power of the radio galaxy in the active phase. So if the jet power is high enough, or it is strong enough to go through the ICM or IGM, then you will see the extended objects, like it will grow up to megaparsec scale. But otherwise, it will be a small angular scale remnant radio galaxy, as I showed one of the sources here. And what was your first question? Sorry, I didn't get the first question.
Yeah, basically, what physical mechanism determine the fading time scale?
Okay, yeah. So it is a combination of synchrotron radiative loss as well as the inverse Compton scattering of CMB photons. So both will both will play the major role in deciding the fading time scale. So the fading time scale is short because on top of synchrotron radiative loss, we have inverse Compton scattering of CMB photons. And since, as I said, that at higher redshift, the CMB photon density is higher, so the inverse Compton ICCMB or inverse Compton scattering of CMB photons will be higher. So the radiative losses will be higher at the high redshifts. And since our sources or these remnant sources reside mostly at high redshifts, so the fading time scale will be even shorter. So
Right.
yeah.
I have a quick follow-up question if I can ask.
Yeah, sure.
So
Okay.
you said-
Okay.
Let's answer some of the questions in the
Okay,
room
sure,
and
sure.
go back to.
Sure,
Okay. Yeah,
Yeah.
go ahead.
Question, but let me probably ask the first one.
Yeah.
So you estimate the magnetic field,
Yes.
right?
Yeah.
But in your equation, there's like one term that I understand. It's something like 1 plus k to the power of like 4/7 or something. What is that k?
This one?
What does it represent?
So this is the ratio of proton by electron. So this is basically, we assume that it is 1. Like it depends on the geometry of the source, but mostly we take this. This is a ratio of proton and electron available in the vicinity of AGN. So basically, you get not only relativistic electrons, you also get the protons, right? So we take them as an equal number of protons and relativistic electrons, right? So we take this ratio as 1 always in our case. But if we see some asymmetry, then we have to take into account all those factors like what do you say that like the baryonic things. What do you say? I'm not very sure about that, but you have to take care of this baryonic evolution with the source. But in very simple assumptions, we always assume k to be 1. Yeah. Yeah.
My follow-up question to you, fit to your SED.
Mhm.
In the case of where you have your 4 data points, your chi-squared seems to be lower than when you had 6 data points. So in that case, you had 1.08, but when you had 6 points for the same.
No, this is not the same
Or
source.
is it not?
Yeah, this is not the same source.
Okay.
Yeah.
That's my.
Okay. So reduced chi-square always depends on how do you fit. So the best fit one is this, and it also depends on the choice of injection index and then magnetic field estimates, everything. Yes. Okay. Yes.
So, do you have any, are there any studies where people compare the spectral ranges for the 7 galaxies in between like 3 galaxies and cluster environments?
So there is no comparison of field galaxies and cluster galaxies, because cluster will always have a different like mechanism, or they go through a different phase in compared to field galaxies, because field galaxies will have what our sample have all the field galaxies. They are not in clustered medium, so they are in low dense environment. So our sources have very low spectral ages compared to the clustered galaxies. So cluster sometimes give you high remnant phase, and they also show some kind of shocks, because when they hit the dense environment, they create the shocks and in the active phase, and when they go into the remnant phase, the shocks will be there in the environment. So there is no direct comparison of clustered and field remnant radio galaxies.
That if field galaxies in a cluster environment,
Mhm.
then it will lose its energy faster because it has to like expand against that cluster dense size.
Yeah, that's what initially was thought. People used to think about this, and then the very same argument what you gave, it was given in a paper what is Perma 2007. The very same reason that in clustered medium, the remnant duration should be shorter. But what we found that it is not the case, because it always depends on the jet power and the environment. So if the environment is less dense, then basically so it is a combination of jet power and environment. If it doesn't encounter with the environment, then it will expand like in an adiabatic manner, or I won't say adiabatic, but it will expand like very rapidly. And then then it will lose its energy faster.
Like, right,
Yes, so it is always biased. Yes, so
they are only residing just environments
mhm. Yes,
but they are not ordinary galaxies.
yes, yes,
They are just high achievers.
correct. So yeah, I forgot to mention that in in clustered environment, as you said, that we have a high power radio source. So yeah, there is a paper, I forgot the author, but there is a paper which suggests that in clustered medium, you mostly get a high power radio galaxies compared to in field galaxies, right? So they are more, so in field galaxies, you get more diffused and amorphous sources, radio sources compared to clustered. Okay. Yes, Zara.
Yeah. So, my first question.
Yeah.
Since redshift is quite important to estimate the linear size and how to interpret your result.
Yeah.
Do you plan to do a follow-up optical sort observation, for instance, for those that have photometric? It's just a matter of test to use the photometric and spectroscopy. Yeah. Then I have another question. If you look at one of the spectral age of the source you present,
This one or
I mean the map was it there is the scale 1, column 1.
which one? Sorry.
Maybe if you still go before this.
Oh, before this. Okay.
It's after, actually.
Is it after
It's
or?
at the
Yeah,
end.
maybe, yeah.
Okay.
It's the one that shows the age.
Oh, spectral age map. You are
Yeah.
talking. Oh,
Yeah.
okay. Okay. Yeah.
So I was expecting that the lower older than the center. Why on the right panel, why do we have the one of 9, 8 metallic closer to the core and the low path 4, 5 metallic? Do you see the
Yeah.
distribution? So what would be the reason for this?
Okay. So here is a backflow of plasma. So it when it hits a medium, then the plasma backflows to the core. So that's why it is near the core. You will see, or near the center, you will see steep spectrum. And steep spectrum and the spectral steep. The older plasma near the center, and so basically this is because of backflow plasma model. So we identified this source, particularly this source, which shows the backflow of plasma. Otherwise, all the sources will give you a gradient, spectral age gradient like this, where you will see at one end you will see as like older, and at one end you will see the younger population. So yeah, about your first question. So these sources have a I-band magnitude of around 23 to 24 mag. So I don't think spectroscopy, you can go with salt, you can go till that. I'm not sure because I'm also not sure about this tracking thing in salt. But if possible, I'll confirm with others. If possible, then we can definitely go for spectroscopic. Yeah.
That the basic catalog.
Yeah, we have seen. So like most of our sample sources are not covered by DC. Yeah. So that's the only problem nowadays because we are struggling to get a spectroscopic redshift information. And since these are at a high redshift, like in photometric redshift catalog, we see them in like they are residing at 2 or more than 1.5. So we are struggling with how to get spectroscopic redshift, but we are trying to get them using some new catalogs. So Mattia has given me a new catalog. I'll try to check whether they are there.
Because Tom's paper, we had photometric and Matthias catalog.
Mhm.
We were able to get spectroscopy.
Yeah. So yeah, so some of our sources have also this So S stands for spectroscopic redshift. So for this source, we have spectroscopic spectroscopic redshift for this one also. This. So wherever we don't get the spectroscopic redshift, we take the photometric redshift. But yeah, I will look at this, and I'm sure if DESI will or some other, I'll check with SALT whether we can do some follow-up spectroscopic to get spectroscopic information. Yeah.
Okay, let's Abhishek, I think you can just ask your
Yeah, sure. Thanks. Actually, it was more like the question that was asked about the cluster environment. So I understand that you have very low sample statistics, but is there any evidence of, environment with respect to the size and remnant timescale? For example, are these galaxies in isolated or are they in cluster environment or so? Do you have a correlation between those?
So yeah, so we have a very we have a correlation, but since our sample size is small, so we cannot say evidently that okay, we have this trend, this is statistical trend that okay, for a field galaxy or for a non-dense environment, we can get the large size or the remnant duration will be short. But yeah, with whatever we have in our sample, we found that for low density environment, the remnant duration is always smaller than the clustered environment, and also the size is larger in case of non-clustered environment. So it is basically obvious with the radiative loss mechanism. So because we are dealing with the synchrotron as well as ICCMB, so the remnant duration will be always shorter than the synchrotron radiation loss. It's alone. So these isolated galaxies will be because we are not here. I want to mention one thing. We are not taking account the adiabatic losses. It can happen that the field galaxies can grow up adiabatically, so it will lose their energy faster. So I'm not sure because we don't have enough population to evidently say that, conclusively say that there is a correlation. But yeah, whatever we found till now suggests that the same.
Right. And is there any specific galaxy properties, for example, star formation rate or, those kind of optical properties that you see for this galaxy, which are different than normal galaxies to be able to produce these remnants?
So mostly they are associated with elliptical galaxies. Whatever studies have been found till now. So the most of the remnant radio galaxies are associated with elliptical galaxies. So they are not gas rich, and mostly the star formation has been quenched in most of the remnant galaxies. But yeah, we cannot say for sure that okay, we have a so also I don't study the optical properties of the host galaxy, but yeah, whatever we have found till now, that most of the optical hosts have this quenched star formation history, and they are old elliptical galaxies. I think this answers your question.
Okay, so I think we ran out of time.
Oh, okay.
Thank you everyone for joining today's lecture.
Thank you so much for inviting me.
Thank you.
Can you stop